Welcome, folks, to Chapter 12 Solids, Liquids, and Especially Gases. We'll start this chapter with playing around with liquid nitrogen and some other liquids and watch how it turns into gas and turns things into solids and sorts of little fun of chemistry of phase changes.
Okay, in here I have liquid nitrogen. I want to see what happens when I add some water. What do we see happening? I add the water. It's starting to smoke violently so the water is chilled down to freezing, and the smoke, and the nitrogen is quickly evaporating or boiling off. And that smoke right there is the boiling gas. So this liquid nitrogen, let's see what happens when we add soap water. It's definitely smoking. Very interesting in itself. But as the liquid nitrogen is evaporating, you can see it blowing bubbles. But on addition, some of the bubbles have actually frozen in the container. So those are crystalline bubbles, frozen in place by the chill. The bottle has been chilled violently with liquid nitrogen, and we covered the surface with foam. See, as I was chilling this, the air inside cooled down. Now that it's starting to warm back up, the air inside is expanding, blowing bubbles, the air expanding and creating this soap bubble on the surface that is going. Sure, I can make it by using my heat hand. I can warm it up much faster, generate these soap bubbles as we see right here.
Okay, we'll start this chapter talking about what it actually is a solid, liquid, and gas, our three major states of matter. While solid is object is considered a solid when the state of matter maintains its own volume and own defined shape, that it's basically stuck in place. Sure, you can spread it out, but it's going to stay clumped together. It's not going to spill over the floor unless there's a round surface where it's going to roll. Has its own momentum. It's going to keep a defined volume. So like a marble is still going to be marble shaped unless you shatter it. Now liquid specifically is a state of matter that, while it has a defined volume, always take the shape of its container. It's always going to spread out to get to the lowest possible level. While a solid you can pile up as a powder, as like a little pile, liquid's going to spread out completely surround a surface, except for some special occasions. And a gas is a state of matter that will adopt both the volume and the shape of its container. That it's going to be as big or as small as whatever it's stored in. I could take all the air in this room and crush it down into the palm of my hand. If I did that, I would suffocate. So, and I don't have that power anyways, but we'll not do that. Now we're going to look at how these will change phases. That when you boil water, it becomes steam. But even so, even when water is not at 100 degrees Celsius, it can still be as a gas known as water vapor. That we can change states of matter by just adding heat or removing heat. When you add too much heat to a solid, it melts. When you add too much heat to a liquid, it boils. If you remove heat from a gas, it will condense back as a liquid. You remove heat from a liquid, it's going to freeze as a solid. We call it fusion in some realms of chemistry. All these ways we can change different phases. However, you can also change different phases through chemical reactions. When you mix and when you combust carbon with oxygen, you form carbon dioxide. It forms liquid. If you take something like gasoline and you burn in oxygen, you can form water and CO2, form a liquid and a gas out of that. So you can change phases of matter just by doing chemical reactions as well. Now, there's a fourth phase of matter we don't really use and we don't really talk about, and that is plasma. But plasma is a state of matter where essentially we take an atom, we strip off the electrons, so it's a positively charged nuclei and free electrons floating elsewhere. There's no set atomic structure, but it takes incredibly high temperatures to do that. So, like the sun is full of plasma. I think the center of an atom bomb generates some plasma, but other than that, we don't really see too much plasma on Earth. Only in specialized laboratories capable of generating it. Some people suggest that lightsabers from like Star Wars are like essentially plasma swords, one way or another. But for the most part, we won't really worry about plasma because it's not something we'll see in everyday life. So, what is actually going on as a solid melts? Now, the atoms are always in motion when we talk about atoms. And kinetic energy is always proportional to the temperature. So that being said, a solid will maintain its shape because the atoms are held together in either ionic bonds or dipole-like bonds. These intermolecular forces are essentially grabbing on and holding these atoms in close proximity, which is why they have a defined volume and a defined shape. They're essentially stuck together because it's like chains or leashes around the atoms. Atom 1 and hold on to atom 2, and they're holding on to atom 3. And so while they can move around a bit, they're not really capable of going very far. But with enough force, you can break them apart. You take a crystal and you hit it with a hammer, you can shatter it, and some of those atoms are going to go flying in other directions, though it's going to largely maintain its solid shape. Now, as energy increases, the atoms will begin to move more. They will rotate. So they'll spin in various directions, whether it's just the atom itself spinning or spinning within the bonds. You have a bond together and they're going to spin. They're going to vibrate. So that's kind of when the bonds bend. So it's like doing yoga poses or they're going like jazzercising. The atoms are moving left and right. They're moving in the groove and they're bending together. The bond angles are all changing and they're going to translate. Translation is just moving front, back, left, right, up and down. So moving in 3 dimensions. The movements are still kind of controlled by these intermolecular forces that are holding them together. But these movements will increase with temperature. and get increasingly more violent, much like a cat on a leash. A short gift from Pinky the cat. That cat is fine. But the atoms are trying to break free, much like Pinky was. Now, when the temperature gets high enough to it reaches the melting point, eventually those atoms will now free themselves. The melting point is simply the temperature at which a solid becomes a liquid. However, the melting point is also the freezing point. So if you heat above the melting point, it begins to melt. If you cool it below the melting point, it begins to freeze. At the melting point, both solid and liquid exist at the same time. Most solids have a very defined melting point where it doesn't really change. Like water freezes at 0. Many solids freeze in the hundreds of degrees, or sometimes even thousands of degrees. But amorphous solids do not have a defined melting point. Amorphous is Greek for amorpha, which means without form. These guys are structures without a defined crystalline shape. They don't have a nice crystal structure with a nice repeating pattern like this. So that means when they melt, they soften up first and then they melt. So it's over a temperature range. Amorphous solids include things like glass. You ever see a guy blow glass? He gets it to a nice, almost molten shape where he can shape the glass however he wants. And as it cools, it will harden into the desired shape. So he gets it almost to the melting point. And so it's soft enough that with a pole or shaping tool, he can kind of squish it like Play-Doh. Plastic is also an amorphous solid. We'll talk about polymers a little bit later, in other chapters, but essentially they don't have a really sturdy structure. They're long chain hydrocarbons, but they're multiple chains that are kind of floppy and they're sort of stuck together, but not really. And so when you heat them, they can kind of flex and you can bend them into certain shapes before they harden again. Now, the same thing's true about liquids. Now, the liquids are like, they have a little bit more freedom than the solids in that, remember, they have a set volume, but no set shape. They're going to be bouncing around over top of each other, but largely held down like crabs in a bucket. They're like crawling all over each other trying to get out, but most of the time, if a crab tries to get out, one crab pulls them back down. They're like balls in a ball pit, like used to be in McDonald's and Chuck E. Cheese before we had all this pandemic. Not that they were ever very sanitary, but they're like largely held in that pit, but you jump in, they're going to go all over the place. They can roll all over each other. They can rotate, they can spin, they can translate, they can move around the ball pit, but they're largely in that ball pit. The only way they can get out is with enough energy. You jump in with enough force, the collision gives them energy to escape. They're held in with intermolecular forces as well. However, these molecules can break free even without being at the boiling point. There is a wide variety of energy in there. Some molecules have lots of energy. Some molecules have very little energy. The molecules with lots of energy that are near the surface can burst free. They can break free of their intermolecular forces and escape into the atmosphere. That process is called evaporation. It is a relatively slow process when it's not at boiling point, but it does occur. There's some evaporation even at 0 degrees. It's very, very little, but there is still some. Once we achieve boiling point, though, when we heat it up enough, all the molecules will have enough energy to break free from their intermolecular forces and adopt a gas. So the boiling point is the temperature at which a liquid can become a gas. cool it down below the boiling point, and the gas will start to condense again. This is usually thought as atmospheric pressure. Once we're at a gas, the molecules are said to be individual particles just bouncing around. They're not really interacting with each other, so they're going to just spread out and just take the entire space. It's like, say, go roam free. Unless you're like a really social butterfly, you're probably going to spread out and find the best place to be. So you're going to spread out and just like you're going to just fill all the available space. Some atoms are going to go over there. Some atoms are going to go over there. You're going to look around for where's the best place to sit. So the gas is going to find the best place, and so it's going to spread out to fill all of the space. So it's going to fill whatever volume and whatever shape of container. Now, there's one more phase change type we can talk about, and that is sublimation. It's a phase change where a solid goes straight to a gas without first passing through a liquid state. This is not too common, but it's something you may have still seen. Dry ice does this. Dry ice is essentially solid CO2. They've chilled CO2 down to an incredibly low temperature such that it formed ice. However, the intermolecular forces are not strong enough to keep it as a liquid. So once it begins to melt, it will escape directly into the gas phase without going through a liquid intermediate. So it'll go from solid to gas. When we condense it, it would go from gas to solid. So going back and forth without stopping in the middle. So after this, we're going to focus almost entirely on gases, because while there is a lot of chemistry that goes on the solid and liquid, a lot of the math that is very well understandable can be treated with gases. So we need to first understand what makes up our atmosphere, what makes up all that. Our atmosphere in itself is a mixture of a wide variety of gases. What we call as air is actually a gas mixture, mostly nitrogen, as you see, 78.1%, a lot of oxygen, 20.9%, and then we get into really trace gases. We have a little bit of argon, a little bit of CO2, some really, really trace gases like methane, the noble gases, hydrogen and nitrogen oxides. And water will play a part in there with its being variable due to humidity. High humidity, that means all the percentages go down, and we have to add water in there. If you have a very dry heat, there'd be very low humidity. Maybe the water percentage is like less than 0.1. So we can't really set that up because depending on where you're at, the water is going to change greatly. But most of these are the same regardless of where you go. Now, we can define our atmosphere by various layers, like an onion. You peel back the layers. Well, the main layer, the one we exist in, is the troposphere. That's the region of the Earth's atmosphere that rises from the Earth's surface and produces all of our weather. That's where we're at. Troposphere is kind of nifty. The humid air will have different water values. We're going to have some different other gas values due to pollution, because that's where a lot of our pollution is, which pollution may contain suspended solids and liquids as smoke and haze. So big city might have a little bit more pollution, a little bit different gas molecules than, say, out in the country. In fact, there's pollution all kinds. Some of it's natural, some of it's not necessarily bad. But you ever go hiking and you're on a mountaintop and you stare over the wilderness, over a bunch of pine trees, and notice it's very hazy in the distance? That's because these trees are giving off their own organic molecules like alpha pinene. Pinene kind of sounds like pine tree, That's because it's a molecule that usually comes from these trees. But those molecules absorb light and create that haze you're seeing. So there's a lot of different molecules that could be in the air, but largely it is what I've said here. Now, as altitude changes, as the height above sea level changes, the characteristics of the air itself will change, including the temperature and what compositions of gas we have. Because the lighter the gas, the higher it can float, as we're going to talk about later. So at the very, very top, you're going to have things like hydrogen and helium at the mostly concentrated up there because they're the lightest gases. But with height also comes a decrease in temperature, at least in the troposphere. Because as we're going up, we're getting further from the Earth's surface, which produces a lot of radiant heat. Heat strikes the surface, is absorbed, and then is reflected back off as infrared radiation that can heat up the surface. As we go further up, you get less radiant heat from the surface, and so it gets colder. So a mountaintop is going to be colder than, say, down low. Now, the next guy is the stratosphere. The stratosphere is a region of Earth's atmosphere that lies above the troposphere and it holds our ozone layer. That is a dry, clear, cold layer. It's about negative 55 degrees Celsius. So that's pretty cold. 0 degrees is where it's freezing. So negative 55 is well below freezing. But something really weird is that in the stratosphere, temperature will actually increase with altitude. That has to do with the ozone layer, and that the ozone absorbs our infrared, or not, ozone absorbs our UV light that, and then it breaks apart. But that prevents the UV light from reaching the Earth's surface, and that's what gives us suntan and as well as it gives us cancer. So this ozone is going to absorb that. As it does that, it's also going to produce heat as it absorbs that light. So as we go higher up in the stratosphere, we have more ozone, we have more light, so we have more reaction, and so we can generate more heat in the stratosphere. Now, the mesosphere, which is the region above the stratosphere, it's largely kind of a mystery to us. The mesosphere begins to cool down again with altitude. In fact, that's the coldest layer in our four spheres. We largely don't know a lot about this mesosphere because it's too high up. The highest plane and highest weather balloon can only really go to the stratosphere. It cannot reach the mesosphere. But and it's too low for all of our like space stations and satellites. Those are up in the ionosphere. So it's kind of like a mystery for the most part. We do send up sounding rockets that can reach the mesosphere and get data for small amounts of time, like several minutes or so. But we don't have anything that can just kind of sit up in the mesosphere. The mesosphere, one cool thing about the mesosphere, though, is that this is where most of the meteors break up as they come down to Earth. If they break up and they don't hit the Earth, they're breaking up largely in the mesosphere. And finally, there's the ionosphere. It's the highest region of Earth's atmosphere. This is where a lot of gases become ionized by the solar radiation. And because of that, this serves as a way to reflect shortwave radio transmission. This is how we can reach other parts of the Earth despite mountains and other things being in the way without the need for satellites. You don't shoot up the radio waves to satellite. It shoots up to the ionosphere, bounces off that, and thus you can reflect it over objects to someone else. Now, if you read about the ionosphere on, say, Wikipedia or something like that, they actually break up the ionosphere into two regions, the thermosphere and the exosphere. But we're not going to really worry about those. But ionosphere is going to, once again, temperature is going to increase with altitude, because you got to think about it, lots of more solar radiation, and we're ionizing some gases. So by doing that, that's going to start heating up the air again. And so we can see it getting hotter and hotter, despite the fact that we're farther up than the mesosphere. We're over 50 miles up. So those are our parts of our air. And we'll talk more about those maybe when we talk about pollution, but that's not for a couple chapters. Now, when we combine the weight of all these gases, if we take an imaginary column of gas and stretch it up all the way to the end of the ionosphere, and we weigh that gas will generate a pressure pushing down on the Earth. Now, this pressure is going to be the atmospheric pressure. It's a definition. The atmospheric pressure is the pressure generated by the combined weight of all the atmospheric gases above any given point on the Earth's surface. So if you take all this air, air has a weight of about 5 times 10 to the 18th kilograms. All this is going to be used to generate 1 atmosphere of pressure, also known as 760 millimeters mercury, or 14.7 pounds per square inch, also known as a PSI. This would be the equivalent of going and diving under the ocean to a depth of 10.3 meters. So you dive that deep, you're going to feel that much pressure on your body. Now, millimeters of mercury is a unit of measuring pressure, the same as atmospheres, bars, and PSI. But millimeters of mercury has a special significance in that it's also named a torr, and it's a literal observation of a physical fact. This was named after Evangelista Torricelli, who was Galileo's secretary during the last few months of his life. Now, he was suggesting that atmosphere has a mass, and because it has a mass, it exerts a pressure. So in 1643, he invented the simple barometer. Barometer is Greek for baros metros, which is weight or pressure, and measure. So measurement of weight and pressure. He takes a glass tube, fills it with mercury to the top, has a finger over it, fully inverts it into a beaker with mercury in it. Some of the mercury leaves the tube, leaving a vacuum at the top of the inverted tube. But not all of the mercury flows out. It doesn't flow out because the air pressure pushing down on that beaker forces the mercury to remain in that tube. And if he measures the height that mercury is flown, that stays in the tube, it is exactly 760 millimeters of mercury. That is the pressure. And so oftentimes we use atmospheric pressure and barometric pressure interchangeably, but they're essentially the pressure of the atmosphere. Now, pressure will actually decrease rather rapidly with height, considering how high up we can go. That at 900 meters, which is about 3,000 feet, not even a mile up, pressure is dropped to 0.9. When we go up a mere, let's see, will that be? A little bit over 3 miles, up, 5,500 meters, it's dropped to 0.5 atmospheres. And it's going to keep dropping as we go higher and higher. So you're going to keep losing the amount of air to breathe as you go higher and higher. So that's why on mountaintops, they often suggest you have a breathing apparatus. It's not that you're out of shape. It's that you literally need to breathe more to get the same amount of oxygen. So if oxygen is 20% of the air and you're breathing half that, you have half as much air to breathe, each breath is going to generate half as much oxygen. So you'd have to breathe twice to get what would normally be one. And that's why you usually have some sort of pure oxygen breathing apparatus as you're trying to mount places like Everest. Now, changes in air density going to lead to changes in weather, as air density are going to create things like the highs and the lows that are going to help predict the weather. That when a high front and a low front collide, we often have various weather changes, tornadoes and stuff, that we can look at the air pressure to help see this. Now, you've probably made some observations about gases in your life. As long as you've driven a car, you've probably seen some of these. That you maybe noticed it's difficult to inflate tires. The more air you put in it, the harder it gets. So oftentimes, the first little bit of air, it's, oh, that's easy. Then more and more, it gets harder and harder and harder because you're getting higher and higher pressures you're generating. If you've ever tried to take the tire pressure, if you take a tire pressure cold versus hot, you're going to have different pressures. So you take a tire pressure early in the morning, you have a low pressure, then you fill it up. Well, then you drive a bit and check it again. It's going to be different, probably higher, because as the tire heats up, it heats up the air within the tire. And so you generate a higher pressure. That they say not to overfill your tires. So when you drive on them and they heat up, the pressure doesn't get too great, so the tires explode violently. You maybe notice hot air causes balloons to rise. But if you put a balloon in a fridge, it will shrivel up, at least temporarily, which will expand back out as soon as you take to warm up. You may have noticed that hot soda will explode more often than cold soda, and it'll go flat faster than cold soda. These observations and more have been made similarly by men of the 17th, 18th, and 19th century. So these scientists observed this behavior of gas and tried to explain it, tried to define this. And we're going to spend a little bit of time looking at this thing. Now, all the laws we're going to see in a minute were succinctly described by our friend Rudolf Clausius over there in 1857. So after most of these people have already created their laws. Now, this is actually maybe a further, there was theories like this before, but Clausius maybe improved on this theory the most, and so he's the one we remember most for it. So he has the kinetic molecular theory of gases. The theory explains how gases behave by assuming they're made up of point-sized, perfectly resilient, constantly moving chemical particles. I'm going to show a quick animation. To take a look. These are, imagine, perfectly resilient billiard balls that only undergo inelastic collisions. That means they bounce off and momentum is conserved. So you notice some molecules are going slow. They collide with a fast-moving molecule. The collided molecule speeds up, and the previously fast molecule slows down. Sometimes they move in other directions. They're just bouncing off willy-nilly without a care in the world. This is how we are understanding gases. To make this work, we have to make two major assumptions. That one, the gas particles have no interactions other than the collisions. There's no attraction, there's no repulsion. They're just bouncing into each other, like billiard balls on a frictionless plane. The balls do not attract each other. That would make pool a lot easier if they did, but they don't. And they are considered to be infinitely small, so they have no volume. They're simply point charges. They're just dots, like one-dimensional particles. They don't have any volume for this to work. And this is when we make these assumptions, a gas is said to be ideal. It behaves in an ideal manner when those two assumptions hold true. In that case, the energy only depends on all the properties only depend on the kinetic energy of the molecules. And kinetic energy only depends on the temperature of the molecules. So we're going to look at the temperature and its effect on kinetic energy and understand what goes on with the volume and the pressure. When we understand pressure, pressure is a force applied on a surface. So pressure is simply the collision of these molecules on the edges of this box, the sides of the container. When the balls hit the side, they generate a pressure. So that's how we're going to think about these particles. However, real gases do occupy a small space, very small, but they do. And real gases do have a small amount of attractions, a minute amount. However, this has to be true. Otherwise, everything would be gas. Nothing would condense into a liquid. Liquid would all be as steam, because if they don't attract, they don't stick together. If they don't stick together, they can't condense. So everything would be a gas, even sodium chloride and steel would be gaseous iron if nothing could condense. So we do have to have some attractions. But this theory does a very good job explaining the ideal gas laws that were discovered many years earlier by scientists such as Boyle, Charles, Gay-Lussac, Dalton, and Avogadro and Henry. So we'll start one by one looking at each of these scientists and what they found. We'll start with Robert Boyle. Mainly he was the earliest of these scientists. Robert Boyle was the 14th child to the first Earl of Cork, Ireland. And in 1657, he read about a new air pump, I guess in a science journal or something. He thought, I can do that. In fact, I can do better. So he improves upon the design. He builds himself a model, and so he starts studying air. Just one of those things where he's like, hey, cool, do this, and I'm going to start changing some variables, just one variable at a time, and see how this affects stuff. So he starts changing the pressure of balloons and seeing how the volume will change based on this air pump. That if you like have some air balloon and you put the changing external and internal pressure, you can see how the volume changes. And so his law simply states that with the temperature and the number of moles of gas, so the quantity of gas held constant, the volume of the gas will vary inversely with the pressure, meaning as the pressure goes up, the volume must go down. As the pressure goes down, the volume must go up. So pressure times volume is equal to some constant K. Well, we can put it as an equation of P1 V1 equals P2 V2, that the pressure and volume at situation 1 are equivalent to the pressure and volume at situation 2. If we want to try to explain this, we can think of it like this. That, remember, pressure are collisions on a container. Well, when you decrease the volume, the size of the container is smaller. And thus, if the molecules are moving equally fast, they're going to hit the sides of the container far more often in a smaller container. And so the pressure must go up. If I increase the size of the container, it takes longer for the molecules to ricochet around. So the average number of collisions will go down. So pressure will go down when the volume is bigger. We will look at an example of some problems with the Boyle's law in just a second. If the pressure of a gas is 760 millimeters of mercury when the volume is 200 milliliters, what would the pressure be if the volume of situation 2 is 325 milliliters? So we're going to set up the expression that 760 times 200 equals P times 325. So to solve for P is equal to 760 times 200 divided by 325. We do that and would get a pressure of 468. 468 millimeters of mercury. Let's do one more. If the pressure is 185 millimeters of mercury and the volume of that pressure is 10 milliliters, what would the volume be if the pressure was to increase to 720 millimeters of mercury? So set up the expression again. 185 times 10 equals 720 times V. Say we solve 185 times 10 divided by 720 would give us our V, which would be 2.57 milliliters. So the volume will have decreased 2.57. Now, our next scientist, Jacques-Alexandre César Charles, a Frenchman, was not always a scientist. He turned from a job in the French Ministry of Finance and then became a scientist. He was the first guy to fill up a balloon with pure hydrogen. And in 1787, he became the first balloonist to ascend with his partner to 3 kilometers in height. But so he did some science looking at how, well, since he's working with balloons and being a balloonist, he working how that the volume would change with temperature. That he found that that with at a constant pressure and a constant number of moles, the quantity and the constant quantity of gas, the volume will vary directly with the temperature. That as he increases the temperature of the gas, the balloon expanded. As you decrease the temperature of the gas, the volume contracted. Now, in 1802, his work was expanded by Joseph Louis Gay-Lussac, not pictured here. We'll talk about him a little bit later, who was a lecturer, a demonstrator at the École Polytechnique. I think we mentioned that earlier when we talked about nuclear chemistry. But he independently discovered that this, and he took Charles' idea a step further, that he found that for every 1 degree of temperature we change the volume by a factor of 1 over 273 degrees. Well, 1 over 273. Now, the Charles law is often called Charles-Gay-Lussac, but since Gay-Lussac has his own law, I think we just call it Charles law for the most part. And so the equation is V equals K times T. However, there's a certain thing that needs to be known, that we cannot use our traditional temperature for this to work. We cannot use a temperature in Celsius or Fahrenheit. If you did that, what happens when the temperature is 0? Well, you would have a volume of 0. What happens when you had a negative temperature? Below 0, you would have to have a negative volume, and that doesn't quite work. So it wasn't until William Thomson, who was going to be Lord Kelvin, he was lauded by Queen Victoria for his work on the first transatlantic telegraph cable, pictured on the right here. He changed how we understand temperature with the discovery of an absolute 0 value. Absolute 0 is the lowest possible temperature. It's negative 273.15 Celsius. He set that a new scale of temperature, which is Kelvin, named after his lordship, Lord Kelvin. Now, 0 Kelvin is the lowest all possible temperature. Remember that temperature is proportional to kinetic energy. More temperature, more kinetic energy. Well, at 0 degrees, all motion stops. All motion stops. So things would perfectly freeze at 0 degrees. So if we had a true ideal gas, only at 0 degrees Kelvin, volume would shrink to 0. However, all real gases would condense long before 0 degrees Kelvin. The gas with the lowest freezing point, helium, freezes at 4.1 Kelvin. So no gas can get that low. And we have never truly achieved 0 degrees Kelvin. We've gone close, but not that close. Now, so the equation is V equals some constant times temperature in Kelvin. That works. With that in mind, we can look at the ratio of volume to temperature at situation 1 to volume to temperature at situation 2. Trying to explain that, remember, temperature is directly proportional to kinetic energy. So if there is a set number of collisions at a set volume, a set temperature, if we were to increase the temperature, we'd increase the speed. So more speed would try to achieve a greater collision. So how do you adjust for that? You give them a greater volume. You wouldn't try to take an Indy 500 to a track and field course. You wouldn't try to drive NASCAR around the track and field 100-meter dash course. It's just not enough space. You need bigger space for higher speeds. We'll show a couple examples of math done with Charles' law in just a second. Let's look at some Charles' law problems. That how would the volume and temperature relate? If the volume of situation 1 is 150 milliliters, when the temperature is 273 Kelvin, what would be the volume of situation 2 if the temperature has increased to 380 Kelvin? I'm going to go ahead and leave this in Kelvin to make our lives a little bit easier. But our equation is V1 over T1 is V2 over T2. So 150 over 273 equals V over 380. Rewriting our expression, 150 over 273 times 380 equals volume. The volume has increased to 208.8 milliliters, or essentially 209 milliliters. That even though if you did this in Celsius, this would be 0, and this would be like, I'd like to say 97 degrees. It seems a really big change in Celsius, but it's only about like a 97-degree change. So it's like a 30% increase as opposed to a crazy big increase in Celsius. Now, Gay-Lussac, as we talked about before, did some other science. He was very well known, this Mitch McConnell looking guy over here, very well known for another law that he's since discovered. He discovered that when you react gases with one another at a constant temperature and a constant pressure, that they will combine in volumes that are related to each other in ratios of small whole numbers. That essentially, I could equivocate volume with a number of atoms. That if I reacted 3 liters of hydrogen, it would completely react with 1 liter of nitrogen. That if I reacted 3 liters of hydrogen and 1 liter of nitrogen, it would generate 2 liters of ammonia. That he found they will react in simple whole number ratios. And this was taken a step further, once again, by our dear friend Avogadro. Now, Avogadro has a hell of a name. Lorenzo Romano Amadeo Carlo Avogadro. He's Count of Corregna and Cerreto. of Italy. Now he would actually relate the volume with moles. His law states that equal volume of a different gas at the same temperature and the same pressure contain equal numbers of atoms or molecules, saying that if I increase the number of atoms, if I have the same pressure of hydrogen and temperature at 1 liter, that has so many molecules. If I have 1 liter of nitrogen, that has the same molecules of nitrogen. So essentially, we can relate volume by a constant to N. If we want to understand that with a set number of collisions and a set speed, more molecules need more space to roam. You can't cram 10 students into 5 chairs. You need to increase the size of your classroom to fit additional students. Same way you have to increase the size of your container to fill in additional number of atoms. All these laws can then be combined together, as we'll see in just a second. Now, all of these laws can be combined together to something called a combined gas equation that we can look at P1, V1, and T1 compares to P2, V2, and T2, assuming the moles are the same. If in situation 1, the pressure is 760 millimeters of mercury, and the volume is 0.80 liters, and the temperature of that situation is 298 Kelvin, what would the pressure of situation 2 be if the volumes was 0.60 liters and the temperature 320 Kelvin? Looking at that, we have 760 times 0.8 over 298 equals P times 0.6 over 320. So rearranging this to solve for P, we would have something like 760 times 0.8 divided by 0.6 times 320 divided by 298. All that equals our pressure, which is going to be our pressure's increase to 1,088 millimeters of mercury. And while the book doesn't discuss this, we can combine Avogadro's law in there to create what is known as the ideal gas law. While we will not physically use this for this book, the ideal gas law states PV equals N R T. That when we combine all the constants together from all the different individual laws, we get an ideal gas constant, which we call R. But this relates pressure, volume, moles, and temperature. How moles is directly related to volume, temperature is directly related to volume, and pressure is indirectly related to volume. But the ideal gas law allows us to look at these 4 variables when and how they relate together. But we will not worry about this at this time. Now, these last 2 scientists, John Dalton and William Henry, are both Brits. While they don't have direct laws that will relate different units together, they do have laws that explain the eccentricities of many gases. That Dalton found a law that kind of fits with the idea of a gas being ideal, that all gases act the same. That law states that the total pressure of a mixture of gas is always equal to the sum of the partial pressures of each gas. So if I have 1 liter of hydrogen and 1 liter of nitrogen, and I put them together, the total pressure is always 2 liters. The total pressure is always 2 liters. If I have a half liter of this and a half liter of that, the total pressure is always going to be 1 liter. Now, most liquids will do that to some extent, but imagine you mix two solids together, two solids of completely different sizes. If I have 1 liter of tennis balls and 1 liter of marbles, and I mix them together, what is the volume of this? It's definitely not going to be 2 liters, because the tennis balls are not going to fit together perfectly. And if they don't fit together perfectly, there's going to be small holes where the marbles can fit in the gaps. And so the volume is going to be larger than 1, but far less than 2. But gases, when I mix these two together at the same volume and the same temperature, you're going to just have a sum of the pressures. And the partial pressure is just the pressure of a gas that it would exert in the absence of all other gases. So the pressure of just one gas. With that in mind, the partial pressure represents just a fraction of the molecules. And so you can actually calculate a mole fraction from there. If we have a total pressure of 3 and hydrogen is generating a partial pressure of 1, that hydrogen is 1/3 of all the number of atoms of the gases that are bouncing around, 1/3 of all the molecules. It's because when you just mix in an ideal gas, it doesn't care what type of gas it is. So you add in more atoms to the same volume, there's going to be more collisions. So they just add up. Well, William Henry, born a few years after Dalton, in the same town Dalton was working for quite a while, like Manchester, would discover a law dealing with solubility of gases, why gases dissolve in solution. His law simply states that at a fixed temperature, the quantity of gas that dissolves in a liquid depends directly on the pressure of gas above the liquid. You have higher pressure above the liquid, more molecules of gas are going to collide with the surface and thus get dissolved into the liquid. Because what has to happen to keep a gas dissolved? The gas has to be trapped with these intermolecular forces within the liquid. Gases tend to have higher kinetic energy than that of a pure liquid, and they're more likely to escape back out. But if there's a higher portion of gas, there's going to be more gas striking the surface of the liquid, and thus more gas trapped in the liquid than would have been normally there. So when you think about a soda, when you first open a big 2-liter container, you have highly pressurized. It's like very taut. There's a little bit of room in the bottle above the surface of the liquid, and it's highly pressurized. You can't really squeeze it. So you open it, here, you see here the air being released. That is high pressure CO2 that's in there. Then you can drink it, you close it back up, and you can seal it, and you can squeeze it for a bit. But over time, it will build up the pressure again. So what has happened? The amount of CO2 in the soda is defined by how much pressure of CO2 is above that soda. When you open it up, Boyle's law says that as the volume of space the gas can be in increases, so you open up, the volume is all the air in the room, the pressure of CO2 will decrease because the CO2 will expand to fit the entire room. You close it back up, you reestablish a pressure, but this pressure is lower than it initially was. So what's going to happen? Lower pressure means more CO2 is going to escape back into the bottle. So it's going to escape into the bottle and thus repressurize it. So the pressure builds up again, and it's going to keep happening until eventually there is no CO2 left and your soda is flat or it's completely drank. Now, why does soda explode? Soda explodes because you essentially a rapid formation of CO2 bubbles. Soda foam is caused by nucleation events. Nucleation is like the growing of things from a seed. You take a kernel and you build around. It's like when you're trying to build a snowman. You take a small little snowball and you roll it in the snow, and it builds up more and more snow as you roll it, and bigger and bigger and bigger until you have a massive snowball, a massive. Well, nucleation is generated by microbubbles that get trapped in the very surface of the liquid. So these CO2 in the air gets trapped in the liquid, and before they get fully dissolved, and they become a place for the bubbles to add in. So the CO2 that is already in solution bumps into that and grows like the snowball, and grows bigger and bigger, bigger, until it can finally escape, breaking out of this. And as it explodes out, it takes some CO2 with it. Well, solids can also act as nucleating agents. If you just add sugar onto the soda, it will start to foam, because the sugar acts as a surface on which the gas can nucleate. Now, the reason why Mentos cause such violent explosions is because Mentos actually have tiny imperfections in the surface. It may not feel like it when you touch the Mentos, but the surface is actually a very irregular, jagged edged candy shell. There's tiny little imperfections that create micro pockets for nucleation. A large surface area with small little divots are perfect for CO2 to build up. And so as you drop those in, you create a large amount of nucleation, which caused that massive explosion. Of course, the reason why diet drinks work better than regular drinks just has to do with the lack of sugar. That sugar will actually slow down the movement of the liquid, and so the CO2 cannot easily get to the Mentos as fast, and so it can't build up as quickly. So you don't have as much pressure buildup that causes the explosion. We can directly apply these same gas laws to our breathing. What is going on in our body as we're breathing in and out? Our body needs glucose and turns this into with the oxygen, and turns this into water, CO2, and our energy. So just looking at our lungs first. Remember, gas flows from high pressure to low pressure. So when you breathe in, your diaphragm it goes down, and your lungs are allowed to expand, creating a low pressure system for air to flow in from the atmosphere. As you exhale, the diaphragm contracts, the diaphragm pushes up, causing the lungs to shrink, creating a high pressure system in the lungs, thus pushing air out. So breathing in and breathing out is just that. As we breathe in, the air flows in, and it flows to the lowest pressure region. As it expands, the lowest pressure region is the alveoli, the little sacs at the very end of the lungs, where we have the interaction with the blood vessels. In those blood vessel in the alveolar sacs, the pressure of oxygen is about 100 millimeters of mercury. So far fewer than normal atmospheric conditions, but good enough. Let's see. Hypothetically, at 20.9, the pressure should be something like 158 in the atmosphere, 158 millimeters of mercury in the atmosphere. So it's a little bit lower than normal atmospheric conditions. However, the blood flowing through is actually a lot less than that. Despite what you might expect, the blood that has been used up, the blue blood, is not bereft of oxygen. It still has some small amount of oxygen. However, only 40 to 45 millimeters of mercury, much smaller than the much lower pressure than what we have in the sacs. And the pressure of CO2 is a little bit higher than what is in the sacs. And so we have an exchange. CO2 leaves the blood and oxygen enters the blood. And of course, the hemoglobin, which is the molecule in the red blood cell, the protein, actually aids with the increase of oxygen uptake. It starts absorbing approximately 1.34 milliliters of oxygen per gram of the hemoglobin. The iron in hemoglobin binds to the oxygen and actually increases the oxygen absorption something like 70 times more than what you would expect by just trying to dissolve oxygen in pure blood. So we get a lot of oxygen into there, flows in. And so we have oxygen-rich blood. Then as the blood flows through, it can go to blood. We can visit various cells within the body. Now, the body tissue cells that are using oxygen have lower pressure oxygen, higher pressure CO2, 30 millimeters of mercury, oxygen, 50 millimeters of mercury, CO2. So once again, CO2 flows out of the cells, oxygen flows into the cells. And this may not be a complete process because you're going through a lot of cells and thus transferring a lot of oxygen at various places. But essentially, we're giving oxygen up and taking CO2 up. And so then flow back through and we repeat and keep this up infinitum as we keep breathing, exchanging out oxygen for CO2, oxygen for CO2. We don't completely use up all the oxygen in our blood, and we don't completely get rid of the CO2 in our blood, but we exchange. Well, in this chapter, we learned about gases, solids, and liquids, and mainly about the ideal gas equation. The ideal gas equation, this equation that states that if we treat gases like an ideal gas, meaning they have essentially no size and no attractive properties, that they would stay a gas under any conditions, we can pretty accurately model a gas so long as we know its quantity, its pressure, volume, and temperature. That as long as we know 3 out of the 4, we're able to correctly measure the 4th. Now, this follows a trend that we'll often find in science, that the real situation is often far too complex to try to model it exactly, and so we'll use a simplified model to understand it in many cases. We talked about pollution, and we'll probably talk about pollution again, and global warming and all that stuff, but it's often far too complex to just oversimplify. That we'll do our best to try to explain what's going on, but most people have to study these things for many years to fully comprehend what's going on, and even then, that may not be the case. We might still be a little in the dark, even if we understand it better than most. So science is often a really complicated thing, and we'll start with a simple model and then slowly increase the complexity until we get it more accurate. Even then, we may not be there, but we'll get asymptotically closer to that perfect line. Now, as I said, ideal gas model assumes gases will always stay gases. If that was the case, we wouldn't exist. Everything on the planet would be a gas. We'd be a gas. Atoms wouldn't never condense into liquids or solids. But that's not the case. So obviously the ideal gas model doesn't work perfectly in all situations. But it works for most gases at most common pressures. So, just example of, hey, models only as the data is only as good as the model, but the model usually works most of the time, which is why we got it in the first place. Just some thoughts to think about. See you in a bit.